Okay, we have this problem on page 406, example 1. We have log 6 something equals log 6 something. The fastest way to do this is to see the pattern. Something equals something, and we have the same base, we have the log, and so the answer is 2x minus 1 equals 11. That's great. How do we do that? Look at the pattern here. If I say x over 2 is equals to 3 over 2, we have same denominator, and the equal sign here, we have same, so x must be 3. So once again, if I say 1 over log x squared is equals to 1 over log x to the b, what is b? Immediately I see the pattern, same, the b must be 2. So that's how I'm doing this one over here. We have log 6, this must be 11. This is the fastest way, I think, to do it. So what we have is 2x minus 1 equals 11. This is just basic algebra. 11 plus 1 is 12. Divide both sides by 2, we have x equals 6. Now be careful. One of the big ideas with logarithms is we need to check our answers all the time. So when we say this is our only answer, we have to be critical here and look for all the restrictions. That's one of the hard things in math, is to remember to reject extraneous solutions. So we remember the rule for logarithms is that when you have log AB, the restrictions is such that a comma b must be greater than 0 and a does not equals to 1. So as long as we respect these restrictions, this answer can be just justified. So what I'm doing here is I'm thinking this here as my b value. This here must be greater than 0. So let me write that down explicitly. 2x minus 1 must be greater than 0 because that's this variable here. And what we have here, the restriction is 2x must be greater than 1. In math algebra, you're allowed to divide both sides with an inequality. We have x is greater than 1/2. And indeed, when we say x is 6, 6 is greater than 1/2, so we say this here is a verified solution. Okay, so we have another problem here on page 406, example 1b. And the nice thing about these log equations is there's more than one way to do it. So let's just play around with this here. We recall that this term here, this positive term, can be thrown to the left. You can actually gather your logs. Let's do that for fun. And we'll say log, and we have 8x plus 4 minus log x plus 1 is equals to 1. We remember the log rules. The log rules says that when there's a minus sign here, we can rewrite it as a division. So we're going to say log, and we're going to divide 8x plus 4 divided by x plus 1 is equals to 1. So this minus sign became a division sign. And this is where we can simplify using basic algebra. When we're looking at this expression here, I can factor out a 4 on the numerator. So log, what we're going to do here is we're going to use giant square brackets so I can see what I'm doing. And we're going to say the numerator is now 4. Just kidding. Okay, so as you can see, it would have been nice if things canceled out nicer, but we're going to go back here. We're going to say the base is 10. We're simply going to rewrite as exponential form. 10 to the 1 is equals to the answer. The answer is always besides the word log. So 10 to the 1 is equals to the answer, which is 8x plus 4 over x plus 1. And this here looks like a very simple algebra question. Just remember that whatever is across the equal sign of logarithms is the exponent. And we don't need the 1 there because 10 to the 1 is 10. Going to multiply both sides by the denominator. So we have 10 times x plus 1 is equals to 8x plus 4. And these x plus 1s cancel out. That's why I don't write it. And we just use distribution here. We have 10x plus 10 is equals to 8x plus 4. We gather our x's. We have 10x minus 8x is 2x. We throw the 10 over. It becomes 4 minus 10 is minus 6. And so x is equals to negative 3. Negative 6 divided by 2 is negative 3. So there's our answer. It's always a good idea to verify your solution. So when we look at this answer, x equals negative 3, it has to work for both statements, this one here and this one here. I'm worried because we have two different situations where it can break down. Let's work on the first statement here. We're going to check our answer. We're saying x equals negative 3. Oh, really? We're going to say log 8x plus 4. And then when you're talking about it, we know that for this term here, this must be greater than 0. That's one of the restrictions of logarithms. So 8x plus 4 must be greater than 0. And what does that mean? 8x must be greater than negative 4. X must be greater than negative 4 divided by 8, which is negative 1/2. X must be greater than negative 1/2. Is negative 3 greater than what negative 1/2? No, it's not. It's less. So we have to reject this question immediately. So therefore, this answer must be rejected even without even looking at this one here. So the answer is no solution. Just for fun, let's check it out over here on the right. We don't have to. We already know this answer is rejected. Just for fun, we're going to say x plus 1. That's this part here. Must be greater than 0. We have x is greater than negative 1. Again, 2 fails. We only need 1 fail, but in this case, we realize that this answer really doesn't work at all. Okay, just for fun, I took that same exact log problem. We have y equals this. We have y equals this on Desmos. That means they equal each other. And visually, we see that they never hit. Now, please don't overtrust your calculator or Desmos. This log graph actually does have an asymptote here, and it goes on towards infinity. It's just that we have some grapher error here, some rounding errors. And visually, it looks like the orange graph never quite touches the black graph here. What's going on here? So I'm just going to meditate a little bit on this part here. You can see that if we factored it, we would have a b-value of 8. A b-value of 8 means the orange graph is 8 times is going to be 8 times as skinny, or you're going to multiply all the x's by 1/8, which is fine. But this base 10 graph and this base 10 graph is vertically the same. They're equivalents. One is not stretched more than the other. So the fact that this orange graph is underneath it in the beginning means it will always be underneath it for infinity. So they never cross. That's kind of a mouthful, but think about what I just said there, and hopefully you agree, at least algebraically, that they never cross. Okay, we have this question here, page 406, example 1c, log 2. And this is tricky here because we have this thing squared. What does that even mean? To attack this question, I recommend you just convert to exponential form right away. We have 2 to the exponent 4 is, and I'm going to put a little square bracket here, the answer. And if you do that, you're going to get it right. We have 2 to the 4 is equals to something squared. Okay, so we have 16 is equals to x plus 3 squared. You're allowed in math to take the square root of both sides. So we have x plus 3, and recall when you square root something squared, it's a variable. It's going to be plus minus square root of 16. So we have the plus minus 4 is equals to x plus 3. And so we get x is equals to, it's going to be 3 plus 4, or it's going to be x is going to be, it's going to be 4 minus 3, or it's going to be negative 4 minus 3. So what is the answer? X is going to be 4 minus 3 is 1 as a possible answer, and negative 4 minus 3 is going to be negative 7. So this is our other possible answer, which we should verify. It's a very good idea to verify your answers. So we're going to verify the answer is 1 and negative 7. How do we verify? Why don't we plug it into this variable here? This, you can call this x, you can call this a, b, c, d, whatever we want. We know that this whole business here has to be greater than 0. That's one of the rules. You have log pq. We know that pq must be greater than 0, so we say this q here must be greater than 0, and that's great. We're going to plug it in here. When we have 1 plus 3 squared, is it really greater than 0? Left side indeed is greater than right side, and so this is legit. 1 plus 3 is 4, 4 squared is 16, 16 is greater than 0, it's legit. Now what about negative 7? We have negative 7 plus 3 squared, is it greater than 0 question mark? And the answer is yes. Negative 7 plus 3 is negative 4, negative 4 times negative 4 is 16, 16 in fact is greater than 0, we say check. So both these solutions are correct. And now we're about to understand this graphically. Okay, so here we punch this exact same question to decimals. We have log base 2, x plus 3 squared, y equals 4. And you can see indeed the point of intersection is x equals 1 and negative 7. So graphically we agree that these are the solutions. Now, just a point of warning, please understand that if you accidentally forget these outer brackets, if you delete it, you'll get a Nike swoosh, which is completely wrong. So when you're using Desmos or your graphing calculator, for example, your TI calculators, it's very important that you plug it in this way. However, when you're working on homework question involving logarithms, please understand that even though the homework question says this, that you can freely drop the exponent and use the logarithm rules freely. Don't overthink it. Just feel free to drop the 2 down. So based off the idea of dropping the 2 down, I just want to analyze this one more time. So let's go back to the paper here. So the original statement was log 2, we have x plus 3 squared equals 4. Now I have a point of warning here. I know that some students here would very freely drop the 2 down using log rules, but this actually changes the question for some strange reason. So yes, algebraically it looks very innocent. It looks very innocent that we can drop the 2 down, and this is what it becomes. But the problem with this is it looks like this is a transformation of the regular log base 2x graph. This is y times 2. This is 3 units to the left, and we know how to sketch y equals 4. This is pretty straightforward. But visually, it's a little bit different. So let me go back to the graph, and I want to compare versus y is equals to log base 2x. So we know how to sketch this. This graph here, logs cut through 1 all the time, and it's like this. We know that this one's a bit taller. This is shifted left 3, so the original asymptote of x equals 0 is shifted left. So we're expecting something that looks like this, that cuts through like that. I'm going to go back to the graph here on Desmos. As you can see, indeed, when I type in x equals negative 3, this here, the right half, is in fact the graph we're expecting. Now, unfortunately, we have a mirror image. This is a little bit of a sneaky question. If you're asked to graph this, just keep in mind that when we have something squared, these negative x values actually do become legitimate just because of the fact that it's squared out. Negative times negative, so we have a negative x value actually does get squared out, so it does produce a legitimate answer. So the entire contents of this q value, or whatever variable you want to call it, is in fact greater than 0. So when you're given an original question like this, the main point is please actually just attack the exponential form right away. Say 2 to the 4 equals this whole business here, rather than use transformations and log rules like dropping like it's hot. Please don't do that. By doing so, we're actually losing a solution. Okay, we have another question on page 408, example 2. We're going to log both sides because we have a variable in the exponent. So we have log 4x is equals to log 605. And the log rule says we can drop it. And so we get x log 4 is equals to log 605. And whatever is beside the x, we just divide both sides. So we're going to divide both sides by log 4. And there we have it. These cancel. X is equals to log 605 divided by log 4. Easy as that. And if you have a calculator, you can even punch it in, especially if you have an old calculator. So I have a relatively new calculator, TI-84. I'm going to press alpha y equals, enter. And I could literally type in log. There's a button called log right here. And it's a nice function. And it magically just produces a number. Remember, log of something is just a number. So log 4. And what do I get? It's 4.62, roughly. So I'm going to say this is 4.62. And one thing to know, however, if you don't have a calculator and you're asked to show some alternate form, another version of this would be x is equals to log 605 base 4. So in general, when we have log some base to the x divided by, okay, so we have this log bx. In general, we can break it down to log x over log b. So this here is equivalent to log x over log b. And what's amazing here is that you can even change the base to whatever you want. I could change it to base 2, I could change it to base 5, I could change it to base pi as well. Even any number as long as it's the same. This is called the change of base rule. So if you're asked to evaluate this here, you may not be able to do it with an older TI-83 calculator just because you don't have this nice notation. However, if you see a question like this, you can simply break it down to two different logs. Log 605 over log 4. However, if you do have a newer calculator, you might even want to play around with it. Press math, and so after pressing math, you can push up, and you'll see this log base. And then now you can see you can just punch it in directly. This is log base 4, push to the right, 605, and we get about 4.62. Okay, we're continuing on with example 2 on page 408. We have this nice question here. We have variable and the exponent. Sounds to me like a log problem. Before we do anything, I'd like to clean this up a little bit. I want to divide both sides by 8. So we have 3 to the 2x is equals to 568 divided by 8 is 71. And now the part with the exponents is much cleaner and simpler. I like it. So we're going to say log left side is equals to log on the right side. It's amazing what we can do with equations. We can add to both sides, we can divide by both sides, we can log both sides. You can do a lot of things to both sides. So we're going to drop the entire exponent, and so we get 2x log 3, remember this is just a number, is equals to log 71. Just as a little aside here, before anybody makes a mistake with the algebra, I'm going to say true or false. 2 log 3 is equals to log 6. Are you allowed to just multiply? And the answer is no, you can't do that. This is false. So please do not just freely multiply this way. So what we have here is using the fact that multiplication is commutative, 2 times 3 is 3 times 2, that you can move things around within when you're multiplying. We're going to write this as 2 log 3 times x. See, I just moved the x to the right here, and we have a coefficient here is equals to log 71. Now we can divide both sides by the coefficient. So I'm going to divide both sides by 2 log 3 is equals to log 71 divided by 2 log 3. And there you have it. We now know what x is. X is equals to log 71 divided by 2 times log 3. Okay, just to wrap this up here, there's many alternate versions of this. I'm just going to evaluate this on my calculator, and you can see that log 71 over 2 log 3 is about approximately 1.94. Now, what's another way of doing this? If you were to choose, for example, a multiple choice test, true or false, is this equivalent to log 71 over, can we throw the 2 back up here? And according to log rules, is that exponent can be dropped back and forth. And so this is going to be log 3 squared, which is the same thing as log 9. And another rule is that you can literally take this and throw it into the base. So this here is equals to exactly log base 9, 71. And that here is a number which happens to be the same as this number here. Alright, we successfully got the answer. Now let's just be silly, just to really be aggressive with these log rules. And so what we have here, we had x equals this business here, but really this is the same thing as x equals 1/2 times log 71 over log 3. And this 1/2 is the answer. It's technically the answer is in the numerator, so you can even move it to the top. So we're going to say x is equals to 1/2 log 71 over log 3. And we know that for log rules, you can drop it or promote it back up to the exponent. So this here is log 71 to the half is the same thing as root 71 over log 3. And just for fun, you can even stick the 3 in there. So what we have is log base 3 root 71. And for fun, you can break it apart. You can say log this over log this, which is log root 71 over log 3. And the hidden base is 10, we could in fact be crazy and make this log base 5 log base 5, and it's also equivalent, the exact same answer. But just to finish this off, I'm going to just choose 3. Now, why did I choose the same number here? Because 3 to the what is 3? This bottom denominator is equals to 1. 3 to the 1 is 3. So why did I do that? We have another form, just for practice, we have log base 371, and that's also equivalent. Okay, example 2c, and we are on page 408. And whenever you see the exponents in the unknown variable in the exponents, we just log both sides. So we have log 4 2x minus 1 equals log 3 to the x plus 2. And this simply becomes an exercise in algebra. You drop them like they're hot, and we have to remember the brackets. That's the key. Will you remember the brackets? Distribution, we have 2x log 4 minus log 4. Distribution, we have x log 3 plus 2 log 3. And the key strategy here is to look at your terms that have x. We want to put all the x's on one side and all the numbers, remember log 4 is a number, on the other side. Now in general, I prefer positive x's. I don't like dividing both sides by negatives. So when I look at the 2x and I look at the x, I feel like I want to move everything to the left, the variable to the left. So I will do that. So we're going to write 2x log 4 minus, so this one here, x log 3 is equals to, I'm just copying this part here, 2 log 3, and I'm going to move this to the right over here, change the sign, becomes a plus log 4. And so as you can see, we have our x's here, and I'm going to factor out the x. What happens? We have x times what is this term here? We have 2 log 4. X times what is this term here? We have a negative log 3. So as you can see, let me just be careful with my brackets here. We have x times 2 log 4 is this one here, x times negative log 3 is this one here, and there we have it. We factored it nicely. And I'm just going to roughly copy this very quickly. And so when you divide both sides by whatever is beside the x here, which is 2 log 4 minus log 3, you can see that the coefficient of x cancels out, and there's your final answer here. Now, are there alternate answers? Let me just evaluate this on my calculator. This is approximately, so as you can see on my TI calculator, I just punched it in, and we get approximately 2.14. Now, is there an equivalent form to this? Let's just play around with it. I'm going to throw this exponent back up. We get log 3 squared plus log 4 all over. I'm going to throw this exponent back up. We get log 4 squared is 16 minus log 3. And I'm just going to rewrite this 3 squared as 9. So this is log 9. And when you have a plus sign, we're going to multiply. So this is equals to log 9 times 4 is 36. And what we have here is when you have a minus sign, we divide log 16 over 3. Are we done? We can even take this base here, this variable here, and stick it into the base. So this here is log 36 to the base 16 over 3. So if the question would have been much harder if we said that this x is equals to log k 36, find k, and the only way you'd be successful in finding k is if you did all the logarithm rules all the way and merged it all to be this answer over here. The k would be 16 over 3. Okay, we have this nice skull equation here. We have skull length in meters is equals to log. We have mass in kilograms. Okay, so what we have is we have this nice equation here, and this is you can think of it as a transformation. And so what we have here is a logarithm graph. You could think of this as your y variable, and this as your x, m. And so what happens is log graphs typically cut through the 1 this way. And what it means is when you shift down by negative 3.44, we have a point here, 1, 0, 1, 2, 3, 4. You can see that the transformation is such that the graph is going to be like this. And what it means is, as the mass of the dinosaur is bigger, the skull size is bigger as well. And of course, we can't have a negative skull size, so we're generally talking about from here and on. And now algebraically, what this means is we have a skull length, S is given as 0.78, and we have this equals to log m minus 3.4444. And this is simply an algebra question. You take a negative term here, throw it to the left, it becomes a positive. So we have log m is equals to 0.78 plus 3.4444. We have 4.22 roughly. So we're going to say log m is approximately 4.2244. And we can very easily solve for m, understanding the exponential form here. 10 to the this is m. 10 to the 4.2244 is approximately m, is m. And so this means that the mass of the dinosaur is greater than 10 to the 3, which is 1,000 kilos. 10 to the 4 is greater than 10,000 kilos. Okay, we have one last problem here, and this is a half-life problem. The challenge is to understand the word problem and to understand it, to write it as this. We memorized that for exponential decay, half-life problems, we set up this formula, and the half-life means we're keeping half. There's your b-value. We don't know what the initial value is. We'll leave it as a naught. However, in the word problem, we say that we keep 49.5%. When dealing with equations, we convert percent to decimal, and we know that the end result is going to be 49.5% of the original amount, which we don't know. And the period, the half-life, is 5,730 years, and so there it is. Algebraically, these cancel out, and we simply log both sides. So we have log 0.495 is equals to log, and what is this, 1/2 to some exponent. And we're just going to use the log rules, drop it down. And so what we get is t over 5,730 log 1/2 is equals to log 0.495, and you divide both sides by log 1/2. These cancel out, and then you multiply both sides by 5,730. So you can evaluate it. T is approximately 5813 years.